Welcome back to day 9 of our coding summer school. And this morning we have Dr. Graeme Pleasance, who's a postdoc researcher in the Quantum Sun group at Stellenbosch University. And he has an MSc in theoretical physics from the University of Birmingham in the UK and a PhD from the University of Sussex. And he's held postdoctoral positions in the quantum research group at UKZN. And currently he focuses on the development of non-perturbative techniques for treating strongly coupled open quantum systems. But today he'll be telling us about ODEs, and you are not here to listen to me. So over to you, Dr. Graeme.
Thank you,
and
Sakile.
Don't forget to use Slack for questions.
Yes. Okay. Yes. Thank you for the kind introduction. So hello everyone. Good morning. I hope you're all doing well. So today, welcome to the Thursday, the morning session of Thursday's lectures. So today I'll be, or this morning I'll be providing you with hopefully a nice introduction to ordinary differential equations. And so the basic structure of this morning session is that there'll be 2 lectures. So in the first lecture, I'll review analytical ways of solving ordinary differential equations and also touching on some numerical techniques for doing this. And then depending on how far we get through the material in this session, either at the end of this session or at the beginning of the next lecture, I'll go over how we can apply the certain numerical methods using the Python package Scipy. So I believe that you haven't been exposed to this yet from your first week's lectures. So I'll review sort of how you some of the content, some of the inbuilt solvers of the Python package Scipy. Okay. So yes, hopefully you can see my screen and everything's okay in your end. Okay. So yes, just a brief outline of the lectures, as I mentioned. So I'll just quickly go over some background and why ODEs are interesting in their own right and where they appear in various areas of science. And then the main bulk of this, the first lecture of this morning will be on analytical methods, so how we can solve ODEs analytically. Also, hopefully applying some of what you learned in the first week's lectures. So in particular, using the Python packages NumPy and matplotlib. So how we can solve these analytically and then plot these solutions using both NumPy and matplotlib. So two particular ways two analytical methods for doing so is firstly using separability of ODEs, and then or 2 types of ODEs that can be solved analytically are separable equations and inhomogeneous first order ODEs. And then towards, again, depending on how quickly I get through the material, then I'll then start discussing numerical methods for solving ODEs. So using in particular the Euler method and the so-called Runge-Kutta methods. And so again, we'll apply some of what we learned in the first week's lectures. So again, using matplotlib and NumPy. And then towards the end of this session or at the beginning of the next lecture, I'll then discuss how we can rather than using these numerical methods by applying these numerical methods by hand, how we can instead just do this more conveniently using the inbuilt ODE solver of the Python library Scipy. And then the remainder of the next lecture will be on how we can solve higher order ODEs. So this first lecture will focus mostly on first order ODEs, and then the next session will focus on how we can solve higher order ODEs. Okay, so so I've kind of mentioned the word ODE. So a good place to start is by saying, well, firstly, what are ordinary differential equations and why are we interested in studying ordinary differential equations? So I'll in the next slide, I'll define more formally what I mean by an ordinary differential equation. But just to start, I would say that, well, the reason why they're interesting is because ordinary differential equations appear in many branches of sciences, so not just physical sciences, but also other things, including, for example, economics, epidemiology, engineering. So, so in particular, ODEs are common when you study so-called dynamical systems. So these are systems whose behavior or properties evolve or exhibit some kind of time-dependent behavior. So the idea is that we have usually some set of laws governing their behavior, and these are usually expressed in the forms of either an ODE or some kind of system of ordinary differential equations. And then the idea is that we can analyze the behavior of our system, so how it evolves, by solving these ODEs. So for example, these ordinary differential equations could describe something like the price of a stock, in economics, and then we solve these to figure out how it evolves in time. So myself being a physicist, one of the first areas in which you are usually exposed to ODEs is when you look at Newton's laws of motion, so in particular Newton's second law of motion. And so, for example, when you examine things like the damped oscillator or damped driven systems, usually the dynamics of these types of systems can be expressed in terms of either first order ODEs or second order ODEs. So in this equation, so this is just an expression for Newton's second law of motion. So here, this is like the mass of a particle, and this x is a vector that determines its position. So again, another example is in population modeling, and perhaps a kind of, at least maybe 2 or 3 years ago, a quite topical example of ODEs appeared in epidemiology. So during the COVID-19 period, one of the kind of basic models of analyzing the spread of infectious diseases is in the so-called SIR model. So what this does is, what this model is essentially is represented by a set of coupled ordinary differential equations. So you have 3 variables, so S, I, and R. So S represents a proportion of a population that is susceptible to a disease. I represents a number of people at a given time that are infected, and then R represents a number of people who recover from the illness. And so by solving these equations, you can get an understanding of how an infectious disease spreads in a population over time. And so on the right-hand side here, this is kind of just an example of a solution to this model. And so you can see here, like the blue line is the susceptible population, which starts at about 50%. And then eventually this gradually goes down as the number of infected people rises, and then eventually these people recover or are removed from the population, and eventually the infection resolves after a certain amount of time. Okay, so a good place to start is by formally defining what I mean by an ordinary differential equation. So essentially, an ordinary differential equation is a group of linear equations that relate some unknown function y. So this is just a real function that just depends on some single variable x. And so the differential equation relates it to its ordinary derivative. So here I use this notation y to the n. So this n here just represents the order of the derivative. So y1 would be its first derivative, y2 would be the second derivative, etc., etc. So in general, this can be mathematically expressed in this way. So this is the kind of general form of an nth, what's called an nth order ODE. And so in this expression, these functions an all the way to a1 and b, we just assume these to be arbitrary differentiable functions. So the idea is that we have some kind of system. Its behavior can be expressed in terms of an ODE or a system of ODEs in this form. And then we want to basically solve these to determine what this unknown function y is to gauge the behavior of our system. Okay, so just to kind of introduce some kind of language that I'll use. That I've already kind of touched upon. So the order of an ODE here labeled by n corresponds to the power of its highest derivative. So for example, a first order ODE is one in which it only contains the first derivative of y and also potentially y itself. So yeah, here, this is just an example of one written here. A second order ODE would be one again, would be one in which the highest order derivative is second order, et cetera, et cetera. So a third order ODE again would be one in which the highest order derivative would be the third derivative of y, and et cetera, et cetera. Okay, so I should also point out that the word ordinary here refers to the fact that this unknown function y only depends on a single variable, which here I call x. So you can also, so there are kind of more general classes of ordinary differential equations, which, so in particular, there are equations called partial differential equations, in which the function that you're interested in solving for can potentially depend on more than one variable. So we won't consider these classes of differential equations here. So ordinary in the sense of y here only depends on one variable x. And so a particular subset of ODEs are called homogeneous ODEs. So those are ones in which this so-called inhomogeneous term b is 0. So in this first equation here, or this first example I provided here, this is what's called a first order homogeneous ordinary differential equation. And there are also a group of ODEs which are called nonlinear. So these are ordinary differential equations where y or any of its derivatives are essentially nonlinear functions. So an example of a nonlinear ODE would be one like, for example, in this form. Generally, so in these lectures, I won't focus so much on nonlinear ODEs just because generally they're much harder to solve than linear ODEs. Although there are a few notable exceptions, so there are some types of nonlinear ODEs which are analytically solvable. So there are one example actually that I'll go over in this lecture. But yeah, just to point out that generally speaking, linear ordinary differential equations are typically can be analytically solvable. Nonlinear ODEs tend to be much harder, and only a very few types of nonlinear ODEs can be solved analytically. In most cases, you can only obtain, for example, like a power series solution to these types of equations. Okay, so for an ODE of order n, the order order n, the solution generally depends on n constants. So if we just look at if on the previous slide I gave the definition, a kind of perhaps maybe not trivial, but a kind of a direct way of solving these types of equations is just by directly integrating both sides of the equation. And if you do that, you can see that for an nth order ODE, if you integrate it, every time you integrate this equation, you're going to generate an unknown integration constant. And so if you do this n times, you're going to generate n unknown integration constants. And so generally, we can, based on that understanding, we can say that a solution to an ODE is unique up to a set of n unknown constants, which we refer to these generally as the boundary conditions. And so in order to obtain a unique solution to an ordinary differential equation, we have to kind of specify extra information that allows us to determine what these unknown constants are. And so this extra information are the so-called boundary conditions. So these are externally imposed conditions on the solution. And so in general, so for an nth order ODE, this could be the value at y at n different x values, any combination of y values, or any combination of values of y, its first derivative, second derivative, etc. So the point about boundary conditions is that they can relate to y or any of its derivatives at any point in the domain of y. Okay, so there's another kind of more specific type of boundary conditions which are known as which relate to what's known as the initial value problem. And so this is the kind of special case when these end boundary conditions are specified at the same initial value of x. So in sciences, it's much more common to usually encounter so-called initial value problems. Typically because, so I mentioned previously that, so in sciences, we're quite a lot of problems fall under the class of so-called dynamical systems. So i.e. we have some kind of system that exhibits some type of behavior, and we have some ODEs that describe this behavior, and then we want to solve these to determine how our system evolves as a function of time. And so usually in these kind of dynamical systems, the only information we have is how our system is initially prepared. And so these, so in this case, the boundary conditions are just the state of our system at the initial time. So for example, in the kind of physics, like if you have like a damped pendulum, these boundary conditions would just be the position of the pendulum at time t equals 0 and its initial velocity or its initial speed, for example. Okay, so an example of like an initial value problem would be something like, so here I've just provided an example of a second order linear ordinary differential equation. And so we can obtain a unique solution to this equation if we specify two boundary conditions. So for example, these could be something like y evaluated x equal to 0 is equal to y0, and the first derivative of y at x0 is this. So in realistic problems, these we would actually specify what these are. We wouldn't just keep these as unknown constants. Okay, so again, just to consider some kind of more explicit examples of ODEs. So yeah, in the beginning, I mentioned population growth being an example of an ODE. So more specifically, this is an example of a first order linear ordinary differential equation. So I've provided also two other examples from physics. So one is in electronics. So we have what's called an RC circuit. So this is a kind of basic circuit that consists of a cell or a cell that can be associated with some voltage V. And then we also have a resistor and a capacitor in the circuit. And so what this first order ODE describes is how the charge across this capacitor changes as a function of time. And yeah, another kind of very common example that you encounter in physics is a so-called damp-driven oscillator. So this is an example of the second order ordinary differential equation. So what this describes is, for example, how the position of an oscillator varies as a function of time. And so in this equation here, you have the first term here relates to, so just to clarify here, x tells us how far our oscillator is from its equilibrium position. So here we have an oscillator which goes backwards and forwards. So it's attached to a spring, and it sort of oscillates backwards and forwards like this, and it's eventually, and its movement is damped by some kind of friction. And so yeah, this first term describes the acceleration of our oscillator. This second term describes friction effects, which generally depend on its speed. And this last term is kind of proportional to the restoring force that's provided by the spring. And we also can potentially have some kind of extra driving term that relates to a potentially externally applied force. Okay, so these are just some kind of examples. So we'll start kind of with now looking at how we can explicitly solve these types of equations, kind of starting with some more basic examples and then building up to slightly more complicated ones. Okay, so a kind of quite basic class of so okay, I'll just say that for the remainder of this lecture, I'll now focus exclusively on first order ordinary differential equations. And so a kind of the most basic kind of class of first order ODEs are ones which, okay, well, generally first order ODE can be expressed in this form. So here we just have G here is just some arbitrary function of y, and H is an extra inhomogeneous term. And so the most basic type of first order ordinary differential equations are those which are called separable. So separable first order ODEs are ones in which can be generally written in this form. And the reason why they're relatively straightforward to solve is because if we just look at this equation, we can separate all terms depending on y and all terms depending on x onto opposite sides of the equation. And then we can basically just solve this equation by directly integrating both sides. So if we know how to integrate both sides of this equation, then that basically just solves our equation. Okay, so an example of a separable first order ordinary differential equation is the one I gave on the previous slide. So this is the one that models population growth. So here we have so what this equation essentially describes is that we have some kind of population. This could be like I don't know, an animal population or something. And so this is what this P here is, just the number of members in our population. And this equation describes how our population changes with time. So it depends on some parameter T, which is time. And so what this equation describes is how it changes with respect to these two kind of parameters K and R. So the kind of the meaning of these, the intuitive meaning of what these parameters will become a bit clearer once we solve this type of equation. And so as I mentioned, because this is a first order ODE, if we want to obtain a unique solution to this, we have to specify one boundary condition, which in this case, so this relates to the initial. So in this problem, this relates to the initial value at p at t is equal to 0, and so we just call it p0 in this case. Okay, so we can just, if we just look at this definition of a separable first order ODE, we can see that we can immediately see that this equation can be written in. So immediately it's not expressed as in a separable form, but we can basically transform it in such a way that we can express it in this form, and then we can solve it by just directly integrating both sides. So the way that we do this is by defining some kind of new variable, which we just call z. And we can see that with this change of variable, if we take this and substitute it into the above equation, and also take its derivative and substitute in the above, then we can basically rewrite this equation in this form. And you can immediately see that this is separable, because we can just divide by z on both sides and then directly integrate, essentially. So by doing that, we then obtain this next line. And just for convenience, so what we have here is just some kind of this log of h here is just an unknown integration constant. And so this just comes from the fact that we're doing an improper integral. So hopefully you know that when you do an improper integral, you have to, when you evaluate the integral, you have to add an extra unknown integration constant. And so here we can just, for convenience, we can, so here this c is our unknown integration constant. We just expressed it in terms of another, we just re-expressed it in this way, which just makes it more convenient to represent the solution. So this can be quite easily solved just to tell us that this is the solution to this ODE. And then if we just transform back to, because obviously we're interested in obtaining p, not z, we can then transform this back to show us that the solution to this this first order ordinary differential equation is given as follows. And just to confirm that this is in fact the solution, you can just take the derivative and show that you in fact recover this equation. Okay, so so here we've just we've determined what this unknown integration constant is, h, by basically just utilizing this boundary condition. So what we can, so more explicitly, what we do is we just substitute t is equal to 0 into the equation, and then doing so we basically get this expression, and then that allows us to determine that h is equal to p0 minus k. And so then this just gives us this, so it gives us this solution in here. And to kind of get a more intuitive understanding of, okay, so this basically tells us how, starting from some initial population P0, how our population changes in time depending on these parameters K and R. So just to get a kind of intuitive feel for this solution, what we can do is we can plot it in using, for example, matplotlib. Okay, so so here on this slide, what I've done is I just included like an example of some code that you can do to kind of plot this solution. And so so here, so hopefully from the first week, I'm assuming now you're all familiar with NumPy and also matplotlib. So so the way that we can plot this solution here. So what this code basically says is that, okay, we can just define a lit, or here we can define a NumPy array of t values. So for example, this just gives us an array of different values of t, ranging from 0 to 50, and having a length of 150. And then what I do here is also define a list of different values of R. So here, again, this is just arbitrarily chosen values. And then I just pick an initial population here that I just set to be 1, and then just set this K value to be 5. So here I call K the equilibrium population and R the growth rate. So from this plot, it will hopefully become a bit more clear why I call this the equilibrium, why I call K the equilibrium population and R the growth rate. Okay, so to kind of plot this solution, what we do is we can define an axis and a figure in the following way, and then what I do here is I basically introduce a for loop that basically that iterates over different values of R. So what I'm doing here is I'm just interested to see how the solution changes when I change R. So if I make R larger or smaller. Okay, and so so what this does here is it just plots. So here, this is just the solution taken from up here. It just plots it for all the values of t in this NumPy array. And so yes, here, so the second line just puts a horizontal, so this kind of black dash line on the right hand side. So the right hand side here is just the figure that's produced from this code. And so this black dash line is just a line which is meant to indicate the equilibrium population. So it's the population that we obtain as t becomes very, very large. Okay, and so so from the plot on the right hand side, we can see how the solution changes with different values of R. So you can see here that as we increase R, the population reaches its long time value, so its equilibrium value faster. And so this kind of indicates why I call R the growth rate. So with larger values of R, our population grows faster, essentially. And so so what we see here is plots of our population with varying growth rates, but with a fixed K. And so hence the reason why all of these solutions reach the same equilibrium value is because we're using the same value of K in all these plots. And so what we can also do is see how our solution changes. So instead of having varying R, we can vary K instead and fix the growth rate. And so just to confirm that this K parameter changes the equilibrium population, I just include another kind of snippet of code here that just essentially does the same thing, but instead of varying R, I'm now varying K. So again, we have another list of, introduce an array of t values, and now we specify a list which contains different values of K. And again, so we have a same initial population, and now a fixed growth rate, which I just set to be 1. And then again, I reused the same code from the previous slide that just plots this solution for different values of k. So this list, this for loop iterates over all the values of k contained in this list. And so we can see here quite straightforwardly, and on the right hand side. So this is again just the figure that's produced from this code, and we can see that as the value of k changes, or I should say that with fixed r, the rate of increase of our population is fixed, but with different k values, it reaches a different equilibrium population. So hopefully this kind of gives you a kind of some insight into how we can use things like, for example, matplotlib and numpy to kind of gain if we're able to, for example, even solve ODEs analytically, how we can still use kind of these computational methods to kind of gain insight into these types of analytical solutions. Okay, so moving on to kind of slightly more complicated types of first order ODEs. So so another class of first order ODEs are ones which are called inhomogeneous first order ordinary differential equations. So these are ones which are generally not separable. So they're slightly more complicated. So they're slightly more complicated to solve. We can't generally solve them in the same way that we did with the previous example. And so they're generally expressed, these types of equations are generally expressed in this form, where P and Q are just arbitrary differential functions of X. Okay, and so the kind of the general way that we can go about solving these types of equations is introducing what's called a so-called integrating factor. So essentially what this integrating factor is, it's just another arbitrary function which we just call I, which we assume to generally depend on this variable X. And so the way we can go about solving this equation is by first multiplying both sides by this integrating factor. And then what we do is, because in principle, this function I that we introduced in principle is arbitrary. And so what we want to do is to solve this equation, what we do is we set a constraint on I and say, okay, we fix I and the left-hand side of this equation after we multiply through by I to satisfy this property, which maybe seems slightly non-intuitive, but hopefully it'll become a bit clearer why we want it to satisfy this property. And so under this kind of, if we impose this constraint, then what we can do is we can just we can directly integrate well, firstly this equation, but then also the second hand side here to get this to this expression. And then what we can do is say, okay, so with this kind of imposed constraint, we can apply the product rule to evaluate this. So again, so this line here is just obtained by applying the product rule. And then if we substitute this back into here, we can then essentially cancel this term and this term on both sides of this equation, and then we're essentially left with this expression here. And so hopefully this now becomes a bit more obvious why we wanted to impose this condition, is because we now get a quite simple equation that allows us to determine what this integrating factor is. And so because this equation is separable, we can just again rearrange I, and we can move I such that I and its derivative only appear on one side and P appears on the other side, and then we can directly integrate this. And by doing so, we basically gain this expression for I, which depends on this unknown function P. And then to kind of solve our problem, what we can then do is just substitute this back into the second line, and then we can just rearrange to get Y. And then this then gives us a general solution up to an unknown integration constant for this inhomogeneous first order ODE. And so we can, so yeah, this essentially, so this at the bottom of the slide, this is just the general form of the solution to an inhomogeneous first order ODE. And so we can see kind of trivially that if we set Q to be 0, then we basically just recover the equivalent solution to the case when the case when this becomes a separable equation. So if we just set q is equal to 0, we can see that this becomes separable, and we can just use the techniques that I showed on the previous slides to then just directly integrate it to get y, and we can see that this solution is consistent with that. Okay, and so just also to clarify some of the notation here. So here, so this expression here just means the improper integral of the terms inside within the integrand. So the way that you would evaluate this in practice is by firstly you have some you'll be given some function p. You can then evaluate this integral as an improper integral without an added integration constant, and then you can evaluate this, and the integration constant is incorporated into this improper integral here. Okay, so hopefully that's kind of somewhat clear. So now we can, as we did with the separable case, we can just apply this. We can apply the solution to some kind of practical examples, and then we'll do the same procedure where we can use, for example, NumPy and Matplotlib to kind of analyze the analytical solution to get some kind of more intuitive understanding on what's going on essentially. Okay, so the example which I kind of touched on earlier was the example of an RC circuit. So this is again just a basic circuit where you have a resistor and a capacitor, which are driven by some time-dependent voltage, which here, so it's here V is our time-dependent voltage, and then we have R and C. So this is the resistance of the resistor and the capacitance, and then we have this Q, which is the variable that we're interested in solving for. Function that we're interested in solving for, and this basically just gives us the charge Q across the capacitor at some particular time t. Okay, and then we also have this kind of initial, to solve this, to obtain a unique solution, we have to then specify this initial boundary condition, which is just expressed in the following way here. Okay, so you can just from looking at this equation, we can kind of immediately tell that it's an inhomogeneous first order ODE. So in this case, where so here the function p of x on the previous slide here is just given by 1 over RC. So in this case, p of x doesn't actually depend on x; it's just a constant. And here our inhomogeneous term is given by this time-dependent voltage. And so, okay, just to kind of to take things gradually, what we can do is start with the basic case where we just set our voltage to 0. And so based on what I said previously, if we do that, this equation now becomes homogeneous. And what that implies is that it is now separable. And so rather than using the solution I gave on the previous slide, we can just use the separability to, again, directly integrate both sides and obtain the solution directly. And so in this kind of special case, we can show that the solution to the charge across the capacitor is just given in this form. And here I just define this new variable, which I call TD, which is just equal to the resistance times by the capacitance. And so the reason I call it T lowercase d is because this kind of sets a kind of decay time scale. So it kind of tells us how quickly the charge in our capacitor is dissipated as a function of time. So this is also kind of illustrated from the code that I've included on this slide. So kind of just doing the same thing as what I did before, we can plot this solution using Matplotlib. So again, this is basically the same as what I did in the previous slides. I just here define a list of various values of this parameter TD. So these are just arbitrary values that I've just decided to use. And so we now have we also specify a list of various t values. So using this linspace function. And then we can just set the initial charge. Again, this is just an arbitrary value. I just set it to be equal to 5. And then what I do here is I do the same thing as I did before. So I'm interested to see how the solution changes when we change the this decay timescale. And so to do this, I just write a for loop that iterates over the different values of TD that's contained within this list. And I plot each of these in the following way. And so, yeah, on the right-hand side, I show the figure that's produced from this code. And so we can see that, okay, so this is just for various values of TD. We can see that by increasing this decay timescale, that the charge across our capacitor decays more slowly in time. And so this kind of illustrates why I call it a decay timescale, is because the larger this value, essentially the longer the rate of change, the rate at which our charge dissipates is slower. So essentially sets, yeah, as I said, it kind of sets a timescale in that way. Okay, so hopefully this is kind of relatively intuitive. And so what we can now do is consider the slightly more complicated example of where we now deal with the full inhomogeneous form of this equation. So when we include the dependence on this kind of driving term, which in this case is the voltage across the circuit. Okay, so we can just play the same game. So what we do is so the general solution. So the general solution to this first order inhomogeneous ODE can just be obtained by applying the solution that I gave on the previous slide. And so what I've done here is I've also made use of this the boundary condition. So if you recall, I said that we just introduce so we say that at Qt is equal to 0, the initial charge is just equal to Q0, which we can just we can specify ourselves. And so perhaps this is an exercise for yourself. So you can show that just by applying this this formula, we can show that the charge in the inhomogeneous case is given in this form. And so we can, to get a kind of intuitive feel again of how our system behaves with this extra driving term added, we can just specify a particular form for this function v. So in this case, I just set it to be a kind of sinusoidal function, where this omega here is, well, it's equal to the frequency of the frequency at which this voltage oscillates. So, or in fact, it's okay. Well, the frequency is given by omega divided by 2 pi, but it's at least proportional to the frequency at which the voltage oscillates. Okay, and so we can plot this solution again. So I just do the same thing, specify the same as create a list containing the same values of this parameter TD. And now I also fix these new parameters, so what I call V0 and omega. So here V0 is like the amplitude of this voltage signal. And so here I just set it to be, I set these to just be arbitrary values more or less. And then I again iterate, so from this list TD, I iterate over the different values of TD to see how now with this inhomogeneous term, how changing this timescale affects the solution. And so so the slight difference here is I now introduce this kind of function which I call integrand. So hopefully from the first week, I'm not sure if you were introduced to lambda functions in Python, but okay, if you're not sure what a lambda function is, it's essentially just it's a basic way of defining functions in Python. So functions being just so it's a function that accepts essentially 2 input variables. So it accepts t and x as these input variables. And so here what this integrand is essentially just the function that's contained inside this integral. And what I do here is I also make use of this sub package of Scipy of the Python library Scipy. So there's a so-called integrates sub package. So basically, this contains a bunch of numerical routines for numerically for performing numerical integration. And so I won't go into too much into the details of this, but there's a particular function from this package that's called quad. So basically, what this does is it just performs a numerical integration. So the way that it works is that it's a function, and you provide it with as an input, you provide it with a function, which is essentially the integrand of which you want to evaluate. So in this case, it's just this term. And so what I'm doing in this line here is just I'm plotting this solution for different values of t. So you can see here that this first term is just this term here. This second term is just this one, but where I'm evaluating this integral using this quad function. So it takes as input this integrand, which I write as a lambda function. And so this t is just the value of t, which it sets the upper limit of integration. So here, obviously, because t is varying, because I'm plotting this as a function of time, then t here is just fixed as each of these t values that I'm iterating over in the for loop. And then this third variable that you specify is the lower bound of the integral. So that's just t, what I call here t is equal to 0. And then this args is just the argument that you're integrating over, essentially. Okay, so the only difference really between this code on this slide and the previous slide is I introduce I make use of this quad function from Scipy. So hopefully this is at least relatively somewhat clear what I'm doing here. Okay, and so then what I can do now is just so on the right hand side, this is just a figure that's produced in the code again. And so now we can see what the effect of this inhomogeneous term is. And so we can see that for relatively short timescales, we get this kind of still roughly kind of exponential decay, like what we saw previously. And so kind of intuitively what this means is that our inhomogeneous driving term isn't having that much effect on the solution. And so kind of the way you can think about this is that what happens is that the charge across our capacitor is decaying fast enough before this driving term is really having an effect. So basically all the charge is gone before this voltage is kind of driving our system, or the time-dependent voltage is driving our system. But then as we see, if we increase these values, this decay timescale such that the charge from this homogeneous term, or the part of the solution that's generated from the homogeneous equation, once TD becomes large enough, we start to see the effect of this driving term. And so here you can see that for the kind of this value of 4, we can see that now we have this kind of oscillatory kind of well, we still have this kind of exponential decay, but now it's overlaid with this kind of this extra oscillatory behavior that comes from this driving term. So in the long time limit, we can still see that this charge basically decays to 0. Okay, so hopefully so far this is kind of relatively clear what I've been doing. And so I'm not sure how much time, I think so. Okay, we have about 10 minutes. So hopefully I should be able to get to a point in which I start talking more about numerical methods, which I'll pick up more on in the next lecture. But just okay, to kind of now to talk about, so okay, at this point I'll just briefly introduce an example of a nonlinear ODE, which is the so-called Bernoulli equation, which is an example of an analytically solvable nonlinear first order ODE. Okay, so essentially this equation is just expressed in the following way. so we can see that it's of a similar form to the inhomogeneous equation that I gave on the previous slide, but now we have this extra y to the power of n term on the right hand side, and obviously we can see that now this is nonlinear because we now have a component in our equation which is a nonlinear in y. Okay, and so to then generally solve this, we again specify some kind of initial condition, which I write as follows. Okay, so I won't dwell too much on this, but just a kind of I will just touch on one way in which you can kind of you can go about solving this equation. Is that you can what we can do is to proceed. What we can do is we can in fact linear. So this is an example of equation that is nonlinear, but which we can linearize by performing a type of variable, a type of substitution. So in particular, what we do is we introduce this kind of this new function which we call z, which we define in the following way. And one can show that using the so-called chain rule, that that if we differentiate both sides of this equation, then we can obtain this expression, and then by substituting this expression into this equation, we obtain this kind of transformed version of the Bernoulli equation. And so you can immediately see here that what this transformation has done is converted this into now a linear first order inhomogeneous ODE. And based on what I said on the previous slide, this is an equation that we can solve analytically. Okay, and so an example for this is if we just set here n is equal to 2, and we just say p and q are just equal to sine x, then the way we can go about solving this is by, so we, so as I mentioned, the way that we can solve first order inhomogeneous ODEs is through this integrating factor. So what I'm doing here is I'm just constructing the general solution to this Bernoulli equation through first evaluating this integrating factor, which, if you recall, was just written as e to the minus integral of p of x. So here we just evaluate our integrating factor in this way. We then just substitute this into the general solution that I gave on the previous slides, and we can show that for this particular example, that it can be that this function z that I introduced can be written in this way, which again, important to emphasize is that you have to include this dependence on this unknown integration constant. Okay, and then because we don't want really the solution to z, we want the solution to y. What we can then do is transform back to show that the general solution to y is given in this form for this particular example. And then if we really wanted to, we could determine what this unknown constant c is by making use of this initial condition. Okay, so that's just that kind of ends the part of the lecture which deals with solving first order ODEs analytically. So now what I'll do is talk about numerical methods. So I'm not sure if now is a good place to stop, or should I, because I think we have about 5 minutes. So I don't know if it would be best to stop now and then restart this in the next section, or should I just quickly start this now? I don't know if there's any suggestions from.
Hello? Yes, you can.
Hi.
Yeah, you can proceed, and then you can stop at 11.
At 11. Oh, sorry. Okay, sorry. I thought it was an hour, not an hour. So it's an hour and a half. Okay, that's fine. So I can. Okay, that's fine. Thank you. Okay, so yeah. So just to mention. Okay, so I mentioned that concludes the kind of the first section, which deals with analytical ways of solving first order ODEs. So now we'll talk about numerical methods, which will then lead into me introducing you to the inbuilt ODE solver of Scipy. Okay, so one of the kind of most basic kind of numerical approaches of treating first order ODEs is this so-called Euler method. And so, okay, our starting point is to say, okay, let's consider the kind of general class of first order ODEs, which can be written in this form. So again, these this could be an inhomogeneous first order ODE. It could be a homogeneous first order ODE. And so one way that we can kind of go about solving this numerically is by kind of constructing a so-called iterative solution to this problem. And so, okay, how do we go about doing that? So what we do is that, okay, if we assume that we're assuming that our unknown function y is analytic, and what that implies is that it emits a kind of a so-called Taylor expansion. And so what this is essentially it's a power series representation of this function y. And so what you can do is by just applying the general formula for the Taylor expansion, you can show that, okay, if this y is analytic, then y evaluated at some arbitrary point, which we call xk, if we then increment this by a small amount, by which we call h, then this is, from the Taylor expansion, this is just equal, we just attain this kind of power series expression, which depends on powers of this increment h. And so, okay, what we now do is we introduce this notation. So here okay, so what you can do is you think about, okay, we have y on our y-axis and x on our x-axis, and then what we do is we kind of split the x-axis up into kind of multiple segments, and each of these segments are kind of separated by a small step that we call h. And so x at each of these segments or steps I label as x of k. And so to get to the next x value, we add h, this h step value to it. So we go, so essentially this is what this is basically just saying. And then I just use the shorthand notation that y at x of k is just yk. And then what we can do is say, okay, from this, in principle, this expansion contains an infinite number of terms. But what we do is we just truncate it and say, okay, if we want to construct a basic, a kind of basic solution, what we do is we at some point we just truncate it up to only first order in this step size h. And so we start from some initial value k, which could in principle be anything. So we have at k is equal to 0, our solution for y evaluated at k0 plus h. So we kind of so okay, we know what, okay, so in general, because I mentioned that to solve a first order ODE, we specify boundary conditions. We know obviously what y0 is, and we know what x0 is. And so we want to now find out what y1 is as we go from x0 to x1. And the way we do this is we just add some small step increment to x. And so, okay, so the way that we determine this from this expression is we say, okay, so we know what at x0, we know what the y value is, it's y0. And then what we do is we truncate this expansion at just the first term. But from this ODE up here, we can just substitute what our first derivative of y is at x0, which is just this f of x0, y0. And then, okay, so based on the fact that we know what y0 is, this gives us y1 at the first x increment. And then what we can do is we can then iteratively obtain other y values of other y values by just kind of proceeding in a similar way. So we obtain y1 from y0, and we say, okay, now we want y2. How do we do this? We just apply this same formula again, which is truncated against this first term. And so you can kind of see what we're doing here is we're kind of constructing an iterative solution. So from knowing what y0 is, we obtain y1. From knowing what y1 is, we obtain y2. From knowing what y2 is, we obtain y3, etc., etc., etc. So we just iterate, and then we basically build up a solution for what y is based on just kind of repeating this kind of this procedure however many times we wish to do so for a particular value of this x increment. So this can kind of more compactly be expressed as a kind of so-called recurrence relation. And so here I've introduced this kind of hat notation. So what this hat notation indicates is that this is an approximate solution to this equation, this first order ODE. And the reason why it's only an approximate solution is because at each step, we're basically truncating this Taylor expansion to just the first term. So obviously there's going to be some kind of error because we're just approximating what the solution to our y is at every step. And so, as I said, the solution to y at some step or to some x value xk is obtained by iteratively starting from some initial x value. And so, as I mentioned, this isn't an exact solution. This is kind of an approximate. This allows us to build iteratively up an approximate solution for y, and we can determine what the error is, or the so-called local truncation error. So what the error, what this local truncation error is just the difference between our exact y value, which is generally unknown, versus this kind of iteratively constructive value of y. And so so just subtracting this expression from this, we can show that this is the truncation error to lowest order in h goes as h squared. And so this just tells us is that when h is very small, then basically this error is proportional to the square of the step size. Okay, so this kind of hopefully illustrates the kind of basic ideas of the Euler method. So the thing I want to stress really with the Euler method is that it provides us with a kind of iterative way to building up an approximate solution to a first order ordering differential equation. And to kind of illustrate this idea, what we can do is kind of consider an example. So, okay, what we can do is revisit this so-called Bernoulli equation, which I introduced on the other side. So, as I mentioned, the Bernoulli equation is a first order nonlinear ordinary differential equation. And so in this example, what I'm doing is I just specify a particular example of this equation. And I say, okay, we want to numerically solve this equation starting with this kind of boundary condition. And then we want to solve this using the Euler method, starting from an x value of x0 to 0 up until some value of x, which I just set to be 0.5 with varying step size. And so based on what I mentioned previously is that the Bernoulli equation is an example of a nonlinear ODE that can be solved analytically by using the method that I demonstrated, so transforming it to a linear ODE. And you can kind of, as an exercise for yourself, you can show that the solution to this equation here is just given in this form. And you can also verify for yourself that this is a solution by just substituting this back into here. Okay, so we want to apply so we have an analytical solution, but we want to kind of demonstrate the idea of this Euler method by now trying to solve this numerically. And so here, what I've done is I've included some kind of Python code which is essentially applies this Euler method to numerically solve the solution. And so how we do this is so what we want to do is first specify a particular step size. And so here, what I do is I just set h equal to be 0.1. From up here, we want to start from the x value of x0 equal to 0. So here I just fix this to be our initial x value. We want to go up to, so we want to apply this kind of recurrence relation that I gave on on the previous slide, up to some value, which, yeah, up to this x is equal to 0.5. So here x max is this final x value. And our initial y value, so our boundary condition, is just y0 is equal to 1. And so what I do here is I start by saying, okay, we just, so here y Euler is just the approximate solution that we get for this ODE. And I initialize this with just, so I write this as a list. So this is a list that just contains a single element. And I just, in this list, I just put our starting value of y0. And what I do is now also write this or define f. So here f, this function f, is just what's contained on the right-hand side of our ODE. So it's just this function y 2 times y to the power of 3 over 2. And so I define this as a lambda function in this way. So here it's a function that has it depends on 2 variables, both x and y. Or actually, in this case, it doesn't actually explicitly depend on x, it only explicitly depends on y. Okay, and so the way that we can kind of manually apply this Euler method is by using a while loop. So from your first week's lectures, hopefully you can recall that a while loop, what it does is it basically repeatedly performs an operation that's kind of contained here up until some kind of condition is reached. So in this case, the condition that we want to reach is that, so we start from some kind of x0 value, we then recursively apply this formula, and then at each step, we basically change the value of x by adding this small kind of increment, this small step size h. And then what we're saying is that once x, repeat this procedure for an arbitrary number of times until our x, this x0 value is greater than x max, and at this point then we then stop, and then what we have now is our solution for y obtained up until our value x max. So here this is now just applying this kind of recurrence relation that I gave on the previous slide. So we obtain y1 by taking our initial value y0 and then adding whatever's on the right hand side of our ODE. So this function in this case evaluated at x0, y0 multiplied by our step size. Then what we do is we just append our value for y1 to this list. And then what we do is we then redefine what y0 and x0 are. So we redefine y0 as y1, and then x0 as x plus our step size. And then essentially this procedure repeats. And so just to also clarify here, the reason that I don't just say x0 is equal to x0 plus h, but kind of use this round function is because so the issue here is that if I didn't use this round, what would happen is that every time I'm adding a value of h to x, this doesn't give us exactly, there'll be some kind of additional rounding error due to the fact that if you add 2 floats together in Python, it doesn't give you exactly what this new value is. It will give you the value plus some kind of very small rounding error. And so this is basically just to ensure the fact that we basically iterate over all values of x. So if we didn't include this, our procedure would stop before x0 gets to x max. So basically we'd be missing the last point in this iteration. Okay, and so essentially if you just run this code, it gets you a list of, our solution will be contained in this list y Euler, and it will just contain all of the values of y for all the with corresponding values of x. And so what we can do is we can then plot this solution, and we can compare it against the the analytical solution that we obtain here. And this kind of gives us an indication of how accurate our method is for different values of the step size. And so if you recall from the previous slide, I said that this is obviously an approximate method. And so at each step, we're kind of approximating the solution by truncating the Taylor series expansion for y up to only first order in H. And so we can kind of tell in that regard that, okay, our solution is probably going to get better if we decrease our step size, because the error is the local truncation error is of the order of H squared. So obviously the smaller H is, the smaller this error is going to be. And this is essentially what is kind of illustrated in these plots. So here, this blue line is the exact solution or the analytical solution that's just given here. And then this orange curve is the solution that's obtained from applying this procedure. So it's the Euler method. It's a numerical solution to this obtained using the Euler method. So you can see that here, starting at relatively large step size, you can see that the numerical solution isn't particularly great. But then as we decrease this step size, it gives us an increasingly accurate approximation of this function. So for a step size of 0.01, you can see that as we go to, as we iterate through, we can see that there's a small error built up, but our numerical solution gives us a relatively accurate approximation of y here. Okay, so this kind of illustrates the kind of basic ideas of this Euler method. So the Euler method, whilst it's kind of quite intuitive to use and quite basic, the issue with it is that in practice it's relatively it's only rarely applied, is because that for the reason that the truncation error is generally the truncation error that you get is generally too generally poorly scales with the step size. So there are other types of numerical methods where this local truncation error scales much more favorably with the step size. And another example of such a numerical method is what's called the Runge-Kutta method. And so this is what I'll now go into kind of what this so-called Runge-Kutta method is. So kind of basic terms, what this is it's kind of a slightly more sophisticated procedure, a numerical procedure for obtaining an approximate solution for a first order ODE. And it kind of relies on, similar to the Euler method, it kind of relies on this kind of iterative way of obtaining our solution, but it does so in a slightly more clever, slightly more sophisticated way. Okay, so just kind of starting from the same point that we did with the Euler method, is that we have a first order ODE of this form, and we want to construct an iterative solution by taking the Taylor expansion of y about some value xk plus h. And so again, this is just what I wrote down on the previous slide. But now what we can do is, so what we did, okay, just to kind of recapitulate, is that what we did with the Euler method is that we took this expansion and we truncated it at first order in H, and then we use this to iteratively build up our solution. So now what we do is we kind of do something similar, but what we do is we kind of add an extra term to our kind of Euler method solution. So what we had for the Euler method is that we had y of k plus 1 was equal to y of k plus f times by our step size. So now what we do is we kind of write down this kind of slightly amended solution. And what you can show is that, okay, if you just if you kind of so if we basically using the same notation as what I did before, so here y of k plus 1 is y of is y evaluated at xk plus h. And then what we can do is we can express this kind of Taylor expansion about x plus h in this way. So to get from here to here, what we do is we just substituted in the fact that, okay, y, the first derivative of y at xk here is just given by this function that's on the right-hand side of this equation. So that's what gives us this term. Then this second term is obtained by taking the derivative of f. And so I've skipped a few steps here, but what you can do is show that this gives you, if you take the derivative of f with respect to x, then it gives you this expression. And what we can do is we can then take the difference of these two to obtain an equation that tells us the local truncation error. So if you recall with the Euler method, the local truncation error scaled quadratically with the step size. But with this kind of new amended approximation, what we can show is that in fact, the local truncation error now scales as the h to the power 3. And so what we can tell is that, okay, this Runge-Kutta method gives us a generally, we can expect it to give us a better approximation, a numerical approximation of the solution, due to the fact that this error, it produces a better scaling with respect to h. So obviously, if h is very small, if the step size is very small, h cubed is going to be generally smaller than h squared. And so based on this intuition, we can then kind of apply this method now in the same way we did the Euler method to check how it performs. Okay, actually, I should specify first that I should mention that on this slide. So this illustrates the kind of the basic idea of this Runge-Kutta method. But in fact, what I've done here is I've performed what's called the second order Runge-Kutta method, or what's sometimes known as RK2. And so what you can do is you can actually go to kind of higher orders. So so more specifically, what I mean by that is, okay, the reason why it's called the Runge-Kutta second order is because basically what it's doing is it's capturing an approximate solution to our ODE, our first order differential equation, up to order h squared. And so in a similar way to the Euler method, this method is applied recursively to obtain our solution for y for across multiple x values. So starting from some x0 and then specifying a particular step size. And so here, the way that this procedure is performed, so the Runge-Kutta is performed, is that, okay, we start from some y0 and some x0. Then what we do is we calculate what these constants a1 and a2 at every x value. And then we use these to determine the next value of y. So this, again, this is kind of just analogous to what we did with the Euler method. Although, as I said, we're doing it in a slightly more sophisticated way. And so this produces an approximate solution which is valid up to order h squared. The Euler method is only valid up to order h. But what we can also do is produce kind of higher order schemes that generally scale better, or the error generally scales much better to higher orders. So again, I won't go over the details of this, but this is just kind of to mention this, is that what you can also do is you can construct what's called a fourth order Runge-Kutta, or RK4, and the way that the solution is constructed here is again, it's done iteratively in the same way, but it's done the way you do it is by defining a kind of it involves more constant. So if you compare this to this one here, you can see that starting from some yk and xk, in order to get yk plus 1, we have to calculate a generally larger number of these constants, which here I call b1, b2, b3, b4. And so this solution is valid to order h4. We can potentially go to higher orders. In principle, we can go to any order, so we can go to h to the power of n if we wanted to. And generally, to the higher order we go, the more accurate our solution, our approximation is going to be the more accurate our solution will be to this first order ODE. But the kind of thing I want to kind of stress is that, okay, you can build these kind of increasingly sophisticated numerical approximations to y, but the idea is that there's a kind of trade-off between accuracy and complexity. So whilst going to higher orders produces a more accurate kind of numerical solution to this problem, as you go to higher orders, it becomes more computationally complex to implement. And so, kind of more specifically, because this Runge-Kutta is applied iteratively, starting from yk to obtain yk plus 1, we have to compute all these values and then use these to determine what yk plus 1 is. And so at higher orders, what happens is that we have to calculate more and more of these coefficients as we go to higher orders, and this can potentially become quite computationally, if we're performing this, if we're simulating this method computationally, at each step we have to store a larger number of these coefficients in memory. And so generally what that means is that this is going to require a larger number of computational resources to implement. So this is just to kind of convey the idea that generally what you want to do is, when you're solving particular problems, is that you want to apply a method that gives you an accurate solution, but one which isn't too computationally intensive to simulate. So not necessarily going to higher orders doesn't necessarily automatically give you a kind of better way of solving these types of equations. Okay, so hopefully that kind of conveys the basic ideas of this kind of Runge-Kutta method, and these, so the second order Runge-Kutta method, and also these higher order, so Runge-Kutta fourth order, etc. And so, okay, to illustrate this idea kind of in more detail, what we can do is apply this to the same problem that we consider with the Euler method. Okay, so we consider the same example that we had before. So we had this Bernoulli equation, or a particular example of the Bernoulli equation, and now we want to solve this using second order Runge-Kutta over the same x interval. So starting from x naught, starting from the value naught up to the x value 0.5 with varying step size. So again, obviously, this equation can be solved analytically. And so what we can do is we can compare our numerical solution to this analytical one to see how well it is able to capture the exact solution with different values of h. Okay, so the code that we use to do this is kind of very similar to the Euler method. The only thing that we change is the way that we calculate yk plus 1 at every step. So the code here that I've included is the same as I did with the Euler method, except all I've done is just changed a small amount of the code that's contained in this while loop. So okay, here, so just to kind of reiterate, so here our solution that we obtain for this first order ODE is stored as a list. So here I call it yrk2. So we initialize this just starting with our value of y at x is equal to 0, which here is y0. And again, so this is just the same function that we had from before. So this is just whatever's contained on the right-hand side of our ODE. And then we construct the solution iteratively in the same way. So we start at y0, x0. We calculate these coefficients. So this a1, a2 are just the constants I gave on the previous slide. So here we're implementing second order Runge-Kutta. So we calculate two coefficients, and then we use these to determine what the value of y is at y x0 plus h. So this is just y1, and then we store this in our list, and then we do the same thing. We just we repeat this by now defining. So our y0 becomes y1, and our x0 is we increment x by an amount h. And again, we round it in this way. due to the reasons that I mentioned previously. And then this while loop this while loop just continues until our x value reaches whatever maximum value of x that we want. So here at 0.5. And so on the right hand side of this slide, again, I've just plotted the kind of approximate numerical solution that we get from applying the second order range cutter against this analytical solution. So again, starting at so we're using the same step size values that I did with the Euler method. And so you can see that again at relatively large step sizes that this that the numerical solution isn't very good. So it doesn't really capture the analytical solution very well. But then as we decrease the step size, so in here, when you just decrease the step size by even a half, you can see that this actually gives a pretty accurate approximation. And then as we go to even smaller values of the step size, it becomes increasingly the numerical solution becomes increasingly accurate at smaller step sizes. And so you can perhaps I can just quickly go back to the Euler here. So you can see that a fixed h value, this orange value, you can see there's still while it's a pretty good approximation, there's still a kind of visible error here. Whilst with the second order range cutter, you can see that this this orange line almost exactly overlaps with the blue one. So this kind of just intuitively illustrates the fact that so what I mentioned was that this second order range cutter is valid up to order h squared and to second order in the step size. And so what that implies is the local truncation error is of order h cubed. And so obviously this is better than the Euler method, which the local truncation error scaled as h squared. And so this is just kind of explicitly illustrated here, is that generally we expect the second order range cutter to perform better than the Euler method, and in fact we see in this example that it does with a fixed step size. Okay, and so I think this is a good place to let me just finish with this slide, and so and then we can stop for a break at 11. Okay, so this is now, so that was the previous so what we did was just we applied the second order range cutter to numerically solve that, to numerically solve an example of the first order of the Bernoulli, a particular example of the Bernoulli equation. So now what we can do is apply the fourth order range cutter, and we just choose a slightly different example. So now this is a slightly different ODE. We can see that it's still a first order ODE, and so we want to solve this with this boundary. We want to solve this initial value problem with this boundary condition. So y at x naught is equal to 1, and so we want to solve this using fourth order range cutter now. Starting from x equal to 0 up to x max is equal to 10 with a particular step size h is equal to 0.5. And so you can see that this is an example of a separable first order ODE due to the fact that we can straightforwardly rearrange this such that y and the left hand side only depends on y, and its first derivative, and the right hand side only depends on x. And you can kind of verify for yourself that by just separating the equation in this way, that you can it can be analytically solved to obtain this solution. So that hopefully this is something that you can perhaps verify for yourself. And so we want to do is play the same game as we did previously. So we want to now solve this numerically using this fourth order range cutter, and then compare our solution to the analytical one to kind of gauge how accurate this method is with a particular step size. Okay, so now so this is just the snippet of code which I used to do this. And so as before, this is just is the same as the code on the previous slides, except obviously here I've now changed this lambda function f is now changed. So this function is just whatever's contained on the right hand side of our ODE. So now this just is this is sine squared times by y. And so again, we implement this using a while loop. And so this time we're implementing fourth order Runge-Kutta. So if you recall that going to fourth order, now we have to calculate more of these coefficients at each increment. So at fourth order, we have to calculate 4 of these coefficients, so B1 to B4. And so these expressions I've just obtained from the previous slide where I introduced the fourth order Runge-Kutta. And so again, the principle here is just the same. The only thing we're doing is that we're just calculating more of these coefficients. But so we calculate these, we then use these to determine what, based on having knowledge of what y0 is, we then use this to determine what y1 is, and then to obtain y2, y3, etc., we then at each time incrementing x by the step size, we then re-specify what our y0 is, and then we just do so this is just the same thing as I was doing on the previous slides. Okay, and so on the right-hand side, I plot this, the solution that we obtained in this way against the exact analytical solution. But what I've also done is, just for kind of clarity, I've also, for this problem, I've also plotted the equivalent solution that you obtain using this Euler method and also the second order Runge-Kutta method for the same step size. So in this case, I've used a relatively large step size, so 0.5, to kind of illustrate the kind of differences between each of these methods. So we can see, so here you can perhaps it's not obvious from the plot, but here I've plotted this analytical solution, which is given by the blue line. And then here I also include the equivalent solution, the numerical solution obtained from the Euler method, second order Runge-Kutta, and fourth order. And you can see here that with the step size, that the Euler, whilst for very small x values, it gives a reasonably accurate approximation. As we iterate through, it gives an increasingly less accurate approximation of our analytical solution. And you can see that this kind of whilst the second order Runge-Kutta is more accurate, it still is a noticeable error, but with this value of the step size, whereas the fourth order Runge-Kutta gives a pretty accurate approximation across all values of x. And this is just based on the same intuition that I mentioned, is the fact that this is to do with the local truncation errors, that obviously as you go to higher order, as you implement this Runge-Kutta to higher orders, the local truncation error scales better with the step size. And so with a fixed step size, you would expect going to higher orders produces a more accurate approximation. And that's essentially what I'm demonstrating here. Okay, and so I think that probably is a good place to stop. So in the next lecture, I'll then go into how, in practice, if you want to solve problems in practice, you don't have to necessarily do it by hand. There are thankfully kind of numerical packages in Python that allow you to do this. So what I'll do in the next lecture is to review the ODE solver of the Python library Scipy. Yeah. So hopefully now we can take I think the 15-minute break.